So the next thing that we're going to do is we're going to talk about how to use the formulas that were given earlier and calculate the future value. So the key is to determine what type of problem you're looking at. So a town has a population of 13,000 and grows at 4.5% every year. What will the population be after 13 years? There's no key words here other than growth. It doesn't say compounded. It doesn't say continuous. So this is going to be a basic growth problem. Now, you don't have to write A of t. You can just write y equals if you prefer. So our growth problem is going to be the initial value, 1 plus r raised to t. And we're going to calculate how much will be there in 13 years. So we have our initial value. Our initial value in this problem is the 13,000. We have our rate. Our rate is 4.5% every year. So that's key, every year. And then they want us to calculate 13 years. So the first thing I'm going to do is I'm going to take 4.5 and I'm going to change that rate by dividing it by 100. And that's going to turn into 0.045. Okay? And I'm going to plug this into my formula. I know that y equals, my initial value is going to be 13,000. 1 plus my rate, we're going to put in that decimal. And we're going to raise it to 13 years. So we're going to calculate how much the population is going to be in 13 years. And we're going to raise that to 13. And we figure out, so we're talking about population, we're talking about people. So it grew to have a future value of 23,039. So it was 38.5. I went ahead and rounded up to 39. All right, so for the next problem, it says an element with a mass of 210 grams decays by 8.3% per minute. How much of the element is remaining after 15 minutes, and round to the nearest 10th gram. So again, no keywords here other than the keyword of decay. So decay means we're going to decrease. So this time we're going to be doing my decay problem. Nothing else. It didn't say half-life. It didn't say compounded. It didn't say continuous. All right, so we have that initial value of 210. We have our percentage rate of 8.3, and we know we're doing it in terms of minutes, so we're going to do 15 minutes. So if I plug this all in, I get y equals, my initial value is 210, 1 minus this time. Now remember, I need to convert that percentage. So we have 8.3% divided by 100 is going to be 0.083. So I'm going to put 0.083 here, and we're going to raise it to 15. We're going to plug it right into our calculator. And I have a really hard time typing in Desmos for some reason. And when we raise that to 15, we get that it decayed into the nearest 10th of a gram. So it decayed to approximately 57.2 grams. So we started with 210, and then after 15 minutes, it went down to 57.2. All right, so next example I have, if you deposit $6,500 into account and it's paying at 8% annual interest compounded monthly, how much money will be in the account after 7 years? So this one says, the key phrase here for this one, and it said it, compounded, and it told you how it's compounded monthly. So we're going to use our compounded formula. So remember, the compounded formula is very similar to the growth formula, except for my rate is divided by the compound and raised to the compound times t. So my compound is monthly. My monthly compound is going to be 12. My initial value is going to be 6,500 at 8%, and we're going to calculate that for 7 years. All right, so we have y equals, so my initial value is 6,500. We have 1 plus 0.08. How do I know it's 0.08? Because if I took 8 and divided it by 100, that's going to give me 0.08. Divide that by my compound of 12, and then that's going to be raised to 12 times 7. So I'm just plugging in everything I know. So 6,000 times, and then I'm going to plug it all into the calculator and Desmos, being very careful that I put it in correctly. Now, if you notice when I did times 7, do you see that it's not in the actual exponent anymore? So you've got to put parentheses around that so that is all in one, and it stays in the exponent. So I had $6,500, but after 7 years, I now have $11,358.24. Why did I do 2 decimal places? Because it's money. Most time money, you do 2 decimal places. All right, so for the next one, it says Joseph invested $16,000 in an account paying 5.7 compounding continuously. So keyword right there is continuously. We know we're going to use that continuous formula. Assuming no deposits or withdrawals are made, how much money do you have round to the nearest cent after 14 years? So this is going to be, he invested. So if he's investing, he's going to be growing his money. So if he's going to be growing his money, then this is going to be a positive rate. All right, so then we have 14 years, and we're going to plug this all into our formula. Now, remember, our formula is going to be our initial value times e raised to kt or rt. I don't really care which one you use. All right, so my initial value is going to be 16,000 times e raised to 0.057, because I'm going to take that and divide it by 100, and times 14 years. So 16,000, and actually I need to put another 0 because I did 1,600. And I can just type in E from the keyboard and it knows what to do. Raise it to, and I'm going to put in parentheses, 0.057 times 14 years. And I get that my investment is going to grow to $35,537.51. All right, so all the key phrases are there. You just have to know which key phrases to look for. All right, so the next one says element X is a radioactive isotope such that every 13 years its mass decreases by half. Right there, half-life. If it decreases by half, that means it's going to be a half-life. Now, given the initial mass of it is going to be 8,800, how much of the element would remain after 25 years to the whole number? Now, here's the key thing. When we do half-life, you are going to start by doing the initial value. Your base is 1/2, and we have the time divided by the actual half-life, okay? So, I have y equals, my initial value in this problem is 8,800 times 1/2. Now, my half-life, it says it right here in this paragraph. It takes every 13 years to half. So, the key is that my half-life is 13 and my time, okay, so my time that they're asking me to calculate is actually going to be 25 years, okay? So the time is 25 years, my half-life is 13 years. And then I would just simply plug it into the calculator once again. So 8,000 times 1/2. And we're going to raise that to 28 divided by 13. So how many years is it going to take for it to, or how much will be left after 25 years? So 13 years is cut in half. Another 13 years is cut in half. Another 13 years is cut in half. So it's going to take it, after 25 years, it is going to have 1,977 grams of that radioactive isotope left. All right, and the last one for a future value. It says, in a lab experiment, 5,300 bacteria are placed in a petri dish. The conditions are such that the number of bacteria are able to double. Keyword there is double. It takes it every 10 years to double. How many bacteria will be there after 12 years? So again, to double, I have my initial value, my base is 2, the time divided by my double. Okay? So my initial value is going to be 5,300 times 2. And we're going to raise that to, we want to do it for 12 years. But it's going to take it 10 years to double. So we're going to divide that by 12. And after that's all said and done, we're going to divide that piece. And we get that there's approximately 12,176 bacteria that is going to double every 10 years, or every 10 hours, not years. So when we look at these pieces, we're talking about 10 hours to double, and it asked us for 12 hours total. Now, these are all future values.